All right, I'm going to go over some of these techniques. Hopefully that'll jog your memory to see what's going on, see how we can break these down. You've seen all this before earlier this year, even way back in Algebra 1, maybe a little bit in geometry. And so in general, things are easy to work with when they're smaller, right? Aren't smaller numbers easier to work with than gigantic numbers just in general? And so same thing's true with a polynomial or an expression. If it's smaller or broken up into tinier pieces, it's a lot easier to perform any type of operations or calculations with it. And so factoring is a term that's used to break something apart, to make it smaller. And so each of these 5 different binomials up here can be broken down into smaller parts, into different factors, meaning things that could be multiplied together to go back to this original form. So each one of them uses this kind of similar technique. There are 2 main techniques up here, but let's just apply them to different types of problems to see how it works. So the very first one we see, x squared minus 49. Now, at first glance, you see an x squared and then you see a number, and you're like, well, there's nothing in common, right? X and 49, they don't have anything in common, so I can't factor that, right? There's no like greatest common factor to pull out or anything. And turns out that this is a special case called the difference of squares, because x squared is a perfect square, meaning I could take the square root of it pretty nicely. And 49 is also a perfect square, right? We can take the square root of 49 very nicely and get a single integer. And it has to be subtraction. That's why it's called the difference of squares, because the word difference means to subtract. So when you see that there's subtraction between 2 perfect squares, you can always factor it into 2 binomials. And the first term in each of these binomials is simply the square root of the first term. So the square root of x squared is just x. And the second term in both of those factors is simply the square root of that last term in our original binomial. So the square root of 49 is 7. And anyone know what I do in between those? What signs do we use? Yeah, use one of each sign. Make one positive and one negative. Okay, so x plus 7, x minus 7. How many of you remembered that? We've done that a couple times right earlier this year. That's good. That's a good one to remember. All right, so I split it up into 2 different things that I can work with, and they're smaller numbers, easier to work with. All right, let's go to the second one, 6x plus 24. Are those perfect squares? 6 and x and 24? No, they're not. And it's not subtraction, right? So that doesn't really matter. But if I look at a 6x and a 24, do they have something in common? Is there some number, some term, or some combination of those that I could divide out of each of those terms? Like, what are both of those divisible by? They're both divisible by 3. Is there a bigger number they're both divisible by? 6 also, right? And I guess you could say they're divisible by 2 and 1, but that wouldn't change it if I divide by 1. And so we would actually want to divide out a 6 because it's not just a common factor, but 6 is the greatest common factor, right? It's the largest factor or term that I can divide out of both of those. So that's a 6. So the way that you factor out a greatest common factor is you write it down outside of a set of parentheses. You bring it out in front. It's kind of like the opposite of distributing something inside of parentheses. You're kind of like distributing that out in front or dividing it out. Now, inside the parentheses, you're going to write those same 2 terms, but after having divided both of them by that GCF. So if I have a 6x, if that was my first term, but I divided it by 6, I'd be left with just an x, right? 6x divided by 6. The 6's cancel out, leaving us with just the x. That second term, 24, well, I could divide that by 6. What is 24 divided by 6? It's just 4, right? Plus 4, positive 4. And so that in blue has been factored. Look at that. It's smaller pieces, smaller components, right? 6 and then an x plus 4, right? 4 is a lot easier to work with than 24. It's a much nicer number. It's been factored, it's broken down. A nice way that you can always check these to see if you factored correctly is if you did multiply it together. Like if I took that 6 and distributed it back in here, would it go up to that original problem? Would it become 6x plus 24? If you do that quick little visualization, you can check, oh yeah, this is definitely right. I know I factored it correctly because it's got to be equal still, right? I'm not changing anything. I'm not adding more to it or dividing something away from it. It's still equivalent. It's the same thing. It's just written in a different form. All right, moving on to this third one, negative 9x cubed plus 72x to the fifth. First off, is this the difference of squares? Because like 9's a perfect square. But what about x to the third? Is x to the third a perfect square? Like, could I take the square root of x to the third or split it up into two equal groups? We can't, right? Because with x squared, I could, because that'd be one x and another x. X to the third, if I tried to split that up, I'd have an x to the second and an x to the first. They wouldn't be equal groups, right? I can't split it right down the middle nicely. And then same thing on the right, 72, that's not a perfect square. So what do you think? Is there anything I can do to this problem to factor it or to make it smaller? Well, if it's not the difference of squares, how about that other type of factoring, binomials? Is there a greatest common factor that I could divide out of both of those terms? Yeah, it looks like there's some stuff in common, right? Now, when you're taking out a GCF, you have to look both at the coefficients, like the numbers that are in front of the variables, and look at the variables themselves. And so let's start just by looking at the numbers, a negative 9 and a 72. Is there some number I can divide 9 and 72 by besides a 1? I heard a 9. Are those both divisible by 9? Yeah. Any numbers bigger than that? Well, no, because 9 is the biggest number that can be divided by 9. So I can divide a 9 out. Right now, the subtraction sign, you can divide that with it or leave it. For our purposes in this example, it doesn't really matter. So I'll just leave that 9 there. Let's just focus on, or leave the negative there. Let's just focus on the numbers. So I'm going to take a 9 and divide that out in front. I'm leaving a little space here intentionally because 9 isn't the only part of the GCF. If I look at both of those terms, we have to look at the variables as well. The first term has x to the third. The second term has x to the fifth. What's the maximum number of x's that I could take out of both of those terms? 3. Right? Don't both of those terms have at least 3 x's available for me to kind of divide out? I couldn't say x to the fifth is the GCF because that first term only has 3 x's, right? It's only x to the third, meaning it doesn't have 5 x's to divide out. But they both do have at least 3 x's available. And so I'm going to take out an x to the third as part of my GCF. A quick rule of thumb is whenever multiple terms or every term in an expression has the same variable, whatever the smallest exponent is going to be part of that GCF. So I see they both have x's, and I'm just comparing the 3 and the 5. Just take the smaller of those numbers, and that'll always be your GCF, right? Even if there were an additional term, like an x to the fourth, well, x to the third would still be the GCF. You have to take the smallest exponent on that same variable. So our GCF is 9x to the third. Now, when I divide that out, remember, you're dividing it, not just like removing it. Think division. So what's going to go inside these parentheses here? That first term was a negative 9x to the third. If I divide that by a positive 9x to the third, what would we be left with? Yeah, there's still going to be a 1 there, a negative 1 in this case because it was negative originally. So we have to make sure, that we keep that 1 in there as like a placeholder. And that has to be there because if I were to distribute that 9x cubed back in, I would need that second term. Make sure you still have 2 terms in this problem once you take out the GCF. On the right, well, 9 x cubed, if I try to divide that out of the 72x to the fifth. Start with the number, the coefficient. And what's 72 divided by 9? Is that 8? Sounds right. That's an 8. Okay, now you had x to the fifth, right? Meaning I had 5 x's. If I took 3 of those x's away, how many would I be left with? Just 2 of them, right? I had 5 x's. I divided 3 out, so we're left with 2. All right, now looking at this expression, it's been factored. It's simplified. My numbers are smaller. I have a 1 and an 8 instead of a 72. My exponents are smaller, right? I used to have an x to the fifth. Now I just have an x to the second and an x to the third. Okay, we've made it smaller. It's more manageable. It's easier to work with. It's been factored. All right, how about this fourth one? 64x squared minus 9. Is there a common factor that I can divide out of both of those terms? Nope. How about difference of squares? Are those both perfect squares on both sides? Yeah, it looks a little different because there's a 64 and an x squared both on the left, but aren't both of those perfect squares as well? 64 is a perfect square, and x squared is a perfect square, and 9 is a perfect square, and it's subtraction. So when you see that right away, you should think difference of squares or difference of perfect squares. So we're actually going to follow the exact same procedure that we did in that first problem with the x squared minus 49. It's going to factor into 2 different binomials. And one's going to be a plus, one's going to be a minus. We know that right away. But now what goes into those 2 spots? And to figure this out, you have to take the square root of each of those terms. Now, when I take the square root of this first term, I'm taking the square root of like each base separately. So what's the square root of 64? It's an 8. And what's the square root of x squared? Just an x. So I know that 8x is my first term in each of those factors, in each of those binomials, each of the parentheses. I have 1 plus, 1 minus. And now for the last term in each of those, we just take the square root again. And what's the square root of 9? It's a 3. So one of these is going to be 8x plus 3. The other is 8x minus 3. And we've factored it. We've broken it down into multiple pieces that are all smaller, easier to work with. Isn't this fun? Yes. Factoring is amazing. And I had to give you this evil one, right? Because that's what I do. Give you evil math problems. What do you think? Can that be factored? Use all the skills that I've won over so far, and I want you to try to factor this one on your own right now. Good, very good. Yeah, if you have already, that's awesome. But I want you to try if you haven't yet. I want you to give an effort. Look at that. Is there a common factor for those? Not really. But I do see subtraction, and I see some perfect squares. Are all of those perfect squares? Could this be another difference of squares problem? So think about what happens if you were to yes. That's nice. So those are correct, but remember one of them is going to be a plus, one of them is going to be a minus. So you have to write 2 of them. Just like on the previous one. Remember here, one's a plus and one's a minus. So you can't write it one time being squared. All right, so this is the difference of squares again, because both sides have perfect squares and there's subtraction in it. So to figure this out, I take the square root of the left side. Only difference is there are 1, 2, 3 terms. And each of these are perfect squares, including those variables, because the exponent is even. All right, and that's something a little bit new for you. You haven't really seen that yet, but I kind of alluded to it with that x to the third, like can you split it in half? So y to the fourth is a perfect square because I can split that into a y to the second times another y to the second. So it is a perfect square. So taking the square root of each of these, I'm going to get 9x y squared plus, and then take the square root of the right side. Square root of 25 is just a 5. That's one factor. My second factor is going to look almost identical to this. It's just going to be subtraction instead of addition. But it's going to be the same terms of 9x y squared. But look, it's now minus 5. By the way, the order that you put these doesn't matter. I could have the subtraction first and the addition second. That won't make a difference because we're multiplying, and order doesn't matter for multiplication, except with matrices. You remember that, don't you? Remember how fun that was? Should we go back to do those? Just like, I could have like a weekend math club, and we could just come here on Saturday morning and just do like all kinds of math problems that you probably forgot about. Anyone up for that? Yeah? No? No. Yes? Okay, great, great. I'm not really going to do it. I didn't think any of you would really say yes. It'd be fun. All right, so that is factoring. Did you remember some of this stuff as we worked through them? Did some of it click a little bit? I hope. All right, so this is the two main techniques for factoring binomials, meaning when there's two terms. But we also have to be able to factor 3 terms. Boom. Can you factor these for me? You're just giving up? Not even writing it down? Come on, you can do this. I believe in you. I'll give you a hint for this first one. You need 2 numbers that multiply to the constant and add to the linear coefficient. Multiply to C and add to B. Can you think of 2 numbers that multiply to 48 and add to 14? Does that sound familiar to anyone, at least that process? We remember doing this? We love factoring this way. It's so much fun. And you're all getting a treat today. You didn't know that we're going to have so much fun in math. You thought it was just going to be another regular lesson. Yeah. Did you notice how this was called factoring preparation? Like, we haven't even begun to think about the lesson yet. But going over this will make the lesson much, much, much easier for you. It actually is a pretty easy concept today, as long as you can factor. Anyone figure it out? 2 numbers that multiply to 48 and add to 14? Brandon, what'd you get? Anyone else get 6 and 8? Does that work? Yeah, so then I would write this as an x plus 6 times an x plus 8. Because 6 times 8 is 48, but 6 plus 8 is 14. By the way, in case any of you are wondering, why do we do it this way? Why is it multiply to one number and add to the second one? Or if you ever forget why, do you remember foiling, first, outer, inner, last, all that jazz for multiplying binomials? X times x is x squared. But when I do x times 8, I get 8x. And then when I do 6 times x, I get 6x. And these two middle terms always are like terms that get to combine, and they're going to be added together. When I add these up, I get 14x. That's why it's 2 numbers that add to 14. And then when I multiply the last terms, 6 times 8, That gives me 48. So that's why it's got to multiply to that last term. So if you ever forget, like, which ones do I multiply to and add to, just think backwards. If you were to multiply those two, think about which ones get multiplied to get that one versus added together to get that middle term with the x in it. So that's really what's going on when we're working backwards this way. So that is the basic factoring. That's the simplest form. You can always use this technique as long as the x squared term has a 1 in front of it, or nothing typically written there. We assume there's just that like invisible 1. So essentially a would be equal to 1. The quadratic coefficient is a 1. Over here in the problem on the right, that's not true. It's a 2. So I can use that same what multiplies to 20 and adds to 13. Because are there any numbers that multiply to 20 and add to 13? You got 10 times 2, but that adds up to 12. Or 5 times 4, but that adds up to 9. They don't add up to 13. The reason it doesn't work that well is because a isn't a 1. It's a 2. Any other number besides a 1 is going to give you trouble. So what do we do in this case? First thing you can try to do, which doesn't work this time, but if there is a number in front of the x squared term, check those other terms and see if they're also divisible by that a. Right? Because if all of these were divisible by 2, I could divide that out in front like a GCF, like we did on the previous problems, and then it'd be really nice because then I'd have an x squared. But not in this case. That doesn't work. 13 is not divisible by 2. So we're using another process. I've called it 5-step factoring before. We're going to have to use something called factor by grouping. Basically, I want to split this 13x up into 2 different terms that add up to 13. But there's a lot of combinations, right? I could use 10 and 3. I could use 14 and -1. There's an infinite number of possibilities. So how do you know which 2 numbers to use? Well, similar to the previous problem, where I started by picking factors of 48, or numbers that multiplied to 48, I'm going to do something similar here, except I'm going to do it by multiplying those other 2 numbers together first, a times c. So 2 times 20 gives me 40. Now you got something to work with. So don't pick 2 random numbers that add to 13. Pick 2 numbers that multiply to 40 and add to 13. Can you think of 2 numbers that multiply to 40 and add to 13? Do 5 and 8 work? Is 5 times 8 40? It is. And what's 5 plus 8? Isn't that 13? And those are the only 2 numbers that would work. So because those are our magic numbers that multiply to 40 and add to 13, I'm basically going to take this middle term, this 13x, and I'm going to write it as a 5x plus 8x. Because isn't that equivalent to 13x? Like, am I changing the value of the problem? No, it's still 13x. I just broke it up into 2 different pieces. Now I'm still going to keep this first term, this 2x squared, and that last term of plus 20. So you only multiply those 2 together just to figure out your initial factors for that middle term. But then for the rest of the problem, go back to that original 2x squared and then the 20. At this point, we have 4 terms. And to factor this, we use a process called factor by grouping. Pretty simple. We just group the first 2 terms together and then the last 2 terms together. And you want to pull the GCF out of each of those groupings separately. So those first 2 terms, there's a 2x squared and a 5x. What do both of those have in common that I could divide out in front? A 2x squared and a 5x. What do they have in common? They both have an x. And so I'm going to write this x out in front. And then in parentheses, I'm going to write those same two terms after having divided out that x. So 2x squared was the first term. If I take 1x away, I'm left with just a 2x. That second term in the first parentheses was a 5x, but if I divided that x out of there, I'd be left with just the 5. Okay, so now we have to look at the second grouping, the third and fourth term on the previous line. That's the 8x plus 20. Do 8x and 20 have a common factor? And we want the greatest one. What's the greatest common factor of 8x and 20 that you can divide out of both of them? A 4? A 2? Do you want the 4 or the 2? We want 4, right? You want the greatest common factor. A 4, a positive 4. And so I'm going to write plus 4, parentheses. Inside the parentheses, I'm going to write those same two terms after dividing them both by 4, the GCF. So 8x divided by 4, well, that's just going to be 2x. What's 20 divided by 4? 5. Does anybody see something magical that happened? Yeah, look at those two binomials now in parentheses. Do you see how they're the same? A 2x plus 5 and another 2x plus 5. If you did this correctly, those two will always match. They're going to be the same. And that tells you that that is one of your two factors in your final problem. And we're trying to break it down. So 2x plus 5 is one factor. Any guesses as to what the other factor is going to be? Yeah, those two GCFs that we divided out in front, an x and a plus 4, well, that's simply your other factor, x plus 4. And so then this right here is the factored form of that original trinomial. We broke it down. We don't have 13 and 20 or an x squared. We have much smaller, much easier pieces to work with. We have the smaller factors, a 2x plus 5 and an x plus 4. Those are like little babies. They're nothing. They're easy to work with. You just tell them, like, go over there, play with these blocks. It's super easy to work with. It's not how I take care of my children, trust me. They have more than just blocks. There's a stuffed animal in there or something. They're great. All right, so that one takes a few more steps, but it's not overly complicated. You all can handle it. Each step one at a time is very basic. Now for the crazy one, right? Whoa, where'd it go? It's so crazy it disappeared. Let's get some room for this one. So negative 5x to the third plus 45x squared minus 90x. We're going to factor this beast of a trinomial. Now, I haven't taught you at all about how to factor something to the third power. So am I that evil that I expect you just to think up some new technique, maybe 7-step factoring that you can do to figure this one out? Or can you use a skill that we've already done on many problems today to make that more manageable and it's something that you do know how? What do you see? Greatest common factor, yeah. All three of these terms can be divided to make them smaller to work with. Negative 5x cubed, 45x squared, negative 90x. What can I divide every one of those numbers by, or every one of those terms by? A 5 and an x. Yes, that's going to make it so much easier. And typically, just a general rule of thumb, whenever you're taking out a GCF, whatever the leading term is, or the term with the biggest exponent, if it ever has a negative sign, take the negative sign with it. Because then what you're left with inside the parentheses will be a positive, which is what we typically want when we factor, if we have to break it down further. So I'm not going to take out a 5x. I'm going to take out a negative 5x, simply because that leading term has a negative. In general, I want you to start trying to think that whenever you see a problem with that negative up front. So negative 5x, parentheses. Inside the parentheses, I'm going to write those same three terms, but I'm going to divide each one by a negative 5x. This first term, negative 5x to the third divided by a negative 5x, is simply going to be an x squared, because negative 5 divided by negative 5 is just a 1. X to the third divided by x is x squared. So that first term is just a nice, easy x squared. We love that. That's awesome. 45x squared now, that second term. Now remember that we divided by a negative 5. So 45 divided by 5 is 9. But because I divided the negative out, it's also going to switch the signs, because it's like 45 divided by a negative is going to become a negative 9, right? A positive number divided by a negative number is negative. And also, if you think about distributing, if I were to distribute that negative 5 back in, a negative 5 times a negative 9 would equal a positive 45. So I know it's got to be negative inside the parentheses. X squared divided by x leaves us with just 1x. And then finally, that last term, negative 90 divided by negative 5. First off, I know that a negative divided by a negative is going to be positive. Anyone know what 90 divided by 5 is? 18, yeah. And then x divided by x is 1. Basically, it cancels out. It's gone. There was 1x. I divided out that x. There are no x's remaining for that last term. And so that crazy, ugly beast of a trinomial becomes this easier one. And now we're done, right? It's factored all the way, right? Gavin? I wanted to take out the negative just because now, if I look inside here, it's a positive x squared. And I can factor this again. But if it were still negative, it wouldn't be the same way. It wouldn't be easy. Whenever we factor, we always want that leading term to be positive. So that's why I specifically want you all to recognize whenever you take out a GCF, look at the leading term. If it's negative, take the negative out in front also to make the first term positive. Because now looking inside the parentheses, can any of you think of two numbers that multiply to 18 and add to negative 9? 6 and 3. Negative 6 and negative 3, right? Because it has to add to a negative 9. But if you multiply two negatives, it'd become that positive 18. All right, so this factors to x minus 3 and x minus 6. But what about that negative 5x? Does that just disappear? Since it was in front of the parentheses originally, it's actually just going to stay there, out in front of the parentheses. And technically, I have three factors. There's the negative 5x, there's the x plus 3, and then there's the x minus 3 and the x minus 6. So we have three separate factors this time, whereas all the other ones, generally, we would just have two. But this is so much nicer and easier to work with. And that's it for our factoring prep. Now we can start our warm-up and then get to our lesson. Yay. Such a good day. Any questions on this, though, before we dive in? But seriously, the lesson is going to go by super quick as long as you're good with your factoring. That's why I spent, 50 minutes on this almost, 40 minutes, whatever that clock says. Be honest, who cannot read one of those kind of clocks? Okay, all right. Just me? What? There was a glare or something, I'm pretty sure. All right, any questions on any of these steps from today? You need to be masters of factoring. Okay, you need to be as familiar with factoring as you are with like adding and subtracting. Which you should be. Again, the more you do something, the easier it gets. First time you learn to subtract, I bet you were like, what is this? But the first time you heard about a negative number, you're like, what? No, there's no such thing as a negative number. But now you use them and you're okay with them. Like we use a bunch of negative numbers here and you didn't even bat an eye. You're like, oh, sure, -5, no sweat. Same thing with factoring. We need to be getting to the point where we've done these so often that you just are able to break it down. Boom. All right, let's start off by talking about fractions. Yay! Whenever you multiply two fractions, it's super, super simple. You simply multiply the numerators together, which means the tops of the fractions, and then you multiply the denominators together, which means the bottoms of the fractions. That's it. Can you multiply these two fractions together, everybody? Go ahead, write it down in your notebook. Multiply these together. It's gonna be epic. All right, let's see how our multiplication skills are. So I'm going to multiply these together. It's going to be one new, like, gigantic fraction. First, if I multiply these, I'm typically going to look at the coefficients first. 2 times 3, that's just a 6. And those other three terms can't be multiplied together. They're different variables, so you're just going to write them all right next to each other. X squared, y to the 6th, z. Down in the bottom, we're going to do something similar. I'm going to multiply the coefficients first. It's going to be a pattern you're always going to be doing. 5 times 8 is 40. And then I've got 3 different variables, so we're just going to put them together. In general, we like to write variables in alphabetical order, just so that we're all putting these the same way. X to the 7th, y to the 2nd, z. Anybody get that far? I hope. Nice and easy. Is there anything else I should do with this problem, though, at this point? Typically, when I see a fraction like this, we should be thinking, simplify it. Same idea. Breaking it down, making it smaller. Yeah, can I make this smaller? So you want to look at each grouping of bases and simplify each one of those. So start with the coefficients. 6 over 40. What can I divide 6 and 40 by? They're both divisible by 2. 6 divided by 2 is 3. 40 divided by 2 is 20. 3 over 20 does not simplify any further. It's as small as it goes. Okay, now look at the first variable, the x's. Where are there more x's, on top or on the bottom? How many more are on the bottom? 5 of them. So x to the 5th goes on the bottom. Where are there more y's, on the top or on the bottom? Up top. How many more are up top? 4 of them, right? I'm comparing 6 to 2. 6 is 4 bigger than 2. And where are there more z's, top or bottom? Same. Anything divided by itself is just 1, so it's gone. We don't even put the z in the problem. And this right here would be our simplified fraction. Anyone get that? Oh, wonderful, you simplified. Good job. I didn't even ask you to do that. That's great. Man, this lesson's going to be lickety-split for you. Did you want a more challenging lesson instead? No, you're okay with that? Okay, multiplying fractions. Pretty simple. So you don't need to write all this down. But just so you know, our first learning target, 8.1, if you want to jot that down at least, it's on operations on rational expressions. I guess the key thing for you to know is when you see the word rational, I want you to think fraction. We already dealt with this term relating to fractions earlier this year when we looked at rational exponents. Remember, that's when you had a fraction in the exponent position, something like x to the 1/2. That was a rational exponent because it was a fraction. So we're going to multiply and divide expressions here that are fractions. Only difference now is there's going to be polynomials in the numerator and polynomials in the denominator, right? We're going to have x squareds and cubes and things like that. And the good news, like this whole part down here, this whole second paragraph, you don't really need to write this down because you already know how to do this. It's just saying when I multiply rational expressions, it's the exact same thing that we just did in that warm-up. It's the same way you've always multiplied fractions. Just like if I had 2/3 times 4/5, that would just be, whoa, this is getting crazy. That would just be 8/15. So as simple as just multiplying numerators with denominators, that's it. It's just going to be bigger expressions, okay? So it's just to put you at ease, lets you know, hey, this is something I'm familiar with already. So here's an example of a rational expression times another one, right? We got some fractions here. Go ahead and write this down. 2x over 3 times x plus 4 over 4. So I'm multiplying two fractions. And all you need to do is treat this like any other problem that you'd ever work with before. If I multiply these, I've got 2x times x plus 4. I just write it right next to each other, right? Doesn't that indicate multiplication? In the denominator, I have 3 times 4. That's just 12. Now notice how I did not distribute in the numerator, right? Could I take that 2x and multiply it by the x in the 4? We could. But we don't want to do that just yet. We want to simplify anything that we can first before we multiply. So looking at this fraction now, look at the numerator and look at the denominator. Is there something that we could simplify in this fraction right now? If I look at the numbers, I see a 2, and there's a 4, and there's a 12. Now, this 4, though, is locked inside of those parentheses. I can't get to that 4, so don't try to simplify that with anything else. It's part of that binomial x plus 4. It's its own separate thing. But the 2 and the 12, those are just individual factors by themselves. I can simplify those. What can I divide 2 and 12 by? Well, we divide them both by 2. In the numerator, if I took 2 and I divided it by 2, I get 1. So it kind of goes away. We would just have the x up there and the x plus 4. In the denominator, we have 12, but I'm dividing that by 2, and I get a 6. And that would be our simplified answer. If you want, you could still multiply that numerator now to make it x squared plus 4x divided by 6. It might look a little bit nicer, but note that this still can't be simplified any further. There are 3 terms, 2 in the top, 1 in the bottom, and all 3 do not have any common factors. So this is it for this problem. We have simplified it in its entirety. What do you think? Are we okay with this so far? It is a pretty basic concept, right? It's just fractions with some variables in it. That's it. Yeah. Great question. You're like, hey, wait, a 4 and a 6, those can be divided by 2, right? The issue is this numerator is technically in parentheses still. Like everything above the fraction bar would have to be calculated first before you divide by the bottom. It's kind of like if I have x plus 2 divided by 2. I can't cancel out those 2's because if I did plug a number in for x, like if I plugged a 1 in for x, when I add those together first up top and then try to divide, I'd have 1 plus 2, which is 3. Then 3 divided by 2 is 1.5. Whereas if I just cancel these out and plugged a 1 in for x, I'd get 1. And clearly 1 and 1.5 are 2 different numbers. So whenever you see a fraction bar, you've got to think about putting everything in the numerator in parentheses and everything in the bottom in parentheses. I'm glad you brought that up. So we can't actually divide the 4 and the 6 over here. Other questions? Why are you laughing at them? Wow, that is so mean. Okay, now this is going to make things easier. Right now, if you look at this problem, it looks a little bit crazy. Right, I've got this trinomial now. An x squared plus 7x plus 12. You're like, oh, I'm going to have to multiply that out. That's going to be a pain. But do you remember what we spent the first 40 minutes of class doing today? Factoring, breaking things down. And here's where it gets really, really cool. To make these a little bit easier, before you multiply anything together, factor everything you can. Factor, factor, factor. So this numerator here on the left, x squared plus 7x plus 12. Go ahead and write this problem down in your notes so you have this example to work with. It's kind of long, but I want you to have this down in your notes so that you can replicate this on your own, so you can see what to do when you're practicing this on your own as homework, which is the work you do at home, which is fun because it's learning and stuff. And we love learning. Man, you're so lucky. Do you know that it's free for you to learn here in high school? Like, that's awesome. Because once you graduate high school, if you want to learn something, like at a college or something like that, you got to pay for it. And you have to pay a lot. But you're getting this for free right now. That's pretty excellent. You're so lucky. Man, I wish I was in high school right now. Learn everything. Am I in high school technically, though? A super senior. Dude, I'm like a super duper quadruple senior then. I do have a high school diploma, though. All right. So before I multiply the numerators together and the denominators together, I want to factor anything if I can. Turns out that trinomial on the left can be factored. Do any of you know 2 numbers that multiply to 12 and add to 7? How about a 3 and 4? So I'm going to write this as x plus 3 and x plus 4, right, over 3x. By the way, this multiplication sign here on the left, when I'm multiplying fractions, you know how we just kind of smush the numerators together and smush the denominators together? Whenever you see that, you can just simply write this as one giant fraction. If you ever see multiplication, because that's really what's going on. I'm multiplying the numerators with each other. I'm multiplying the denominators together. So I'm actually going to extend this fraction line here on the right. I'm going to multiply by simply writing that other numerator, that 9x, just right next to those first two factors, because that's what it would look like to indicate multiplication. They'd be right next to one another. Same thing in my denominator, 3x times x minus 16 squared. Hey, can I simplify that x minus 16 squared, do you think? It kind of looks like a difference of squares, doesn't it? But is it actually a difference of squares? Not really. 16 is a perfect square. It is subtraction, but that x is not being squared currently, so we can't do anything with it. And I can't just distribute that exponent either, because I'd have to multiply them side by side and then like FOIL it out or whatever. So we're going to leave that as x minus 16 squared. All right, does anything cancel out? I've got an x on top and an x on the bottom. Those would cancel out. That would divide out to be 1. Looking at coefficients or numbers, I've got a 9 and a 3. Now, 9 over 3 simplifies to 3 over 1. Right? 9 divided by 3 is just 3. So I'm going to rewrite this and just kind of rearrange it. Parentheses, x plus 3 times x plus 4. And in the denominator, I'm just going to have this x minus 16 squared. And that's that. Questions yet? All right, go ahead and try this one on your own. So you have 4x minus 6 over 5x plus 15. That's one fraction. And it's being multiplied by 10 over x minus 3. Now, before you multiply those together, can you break any of those down? Can you factor any of those? So look carefully at the numerator and denominator on the left. And think about GCF factoring. So that first fraction, think about the GCF. We take a 2 out. That leaves us with 2x minus 3. In the denominator, we can divide a 5 out. That leaves us with x plus 3 times, and so remember, just for multiplication, I'm not going to write that times symbol or the multiplication symbol. I'm just going to write that other fraction kind of right next to it. Write the 10 over x minus 3. Just make sure that you put any binomials in parentheses. Now there are going to be some of the coefficients that simplify or cancel out. You can simplify them now or do it later. So right now I'm going to take the 2 and the 10 and multiply them together to get 20. That leaves me with 2x minus 3. In the denominator, I've got 5, x plus 3, and x minus 3. So just kind of grouped all the coefficients together in the fronts. And now I see 20 over 5. I can divide that out, right? That simplifies. What's 20 divided by 5? It's just a 4. So we're going to write this as 4, 2x minus 3 divided by x plus 3, x minus 3. I'm going to bring that up for you. Can I cancel out the x minus 3's? It looks close, doesn't it? Really, really similar. But one of them has a 2 in front of the x, the other one doesn't, meaning they are different. So I can't cancel those out. In fact, there's nothing else I can do at this point. So this would be multiplied together. That's it. It's a crazy fraction. There's still variables, but that's what we get when we would multiply them out. We doing okay so far? Okay. I'm going to give you like 2 minutes to write this problem down and then take your time factoring everything and then seeing what cancels out. Okay, there's going to be a lot of stuff that cancels here. This is kind of putting all of this together for multiplication. So take your time writing every single one of these down. And then when you start to factor these, you're going to have a GCF that can divide out of 3 of those. And after you take out that GCF, then you're going to have just your standard factoring, like reverse FOIL, what multiplies to the constant and adds to the linear coefficient. So this is going to be really good practice for you to make sure you've been following along with everything we've been going through today, putting it all together. I'm going to start factoring this with you. And I'm thinking this as 4 separate trinomials. We're going to factor each one of them. That first one, I see a 2, 8, and 10. Those are all divisible by 2. So I'm going to start by writing a 2 out in front. That leaves me with an x squared minus 4x minus 5. That's just taking out the GCF. Over its denominator, I see 4, 16, and 12. Those are all divisible by 4. So I'm taking out the GCF of 4, which leaves me with x squared plus 4x plus 3. And again, this is multiplication, so I'm just going to kind of extend that fraction bar because it's all going to be smushed together at the end. So now let's look at the second numerator. I see 2, 6, and 36. Those are all divisible by 2. That leaves me with x squared minus 3x minus 18. And that last denominator on the right, it doesn't have a GCF, right? X squared, 11x, and 30. So I'm just going to put that in parentheses. X squared minus 11x plus 30. So those are those same 4 trinomials, but I factored the GCF out of each of them. At this point, I now want to look at each of those trinomials, and we're just going to factor those with that basic reverse FOIL. So this is where you ask yourself, hey, what 2 numbers multiply to the constant, c, and add to that linear coefficient, b? Now, anything that we already took out front, any GCFs like that 2, is still going to stay there. But now I need 2 numbers that multiply to -5 and add to -4. That's a -5 and a +1. That first denominator, the 4, is still out in front. But now look at that trinomial in purple. I need 2 numbers that multiply to 3 and add to 4. 3 and 1 work, yeah. X plus 3, x plus 1. Now go to that second numerator that I have in green. That 2 is still out in front. I need 2 numbers that multiply to -18 and add to -3. A -6 plus 3 would work. So x minus 6, x plus 3. And finally, in blue, that last denominator, we need 2 numbers that multiply to 30 and add to -11. Okay, both negative, right? X minus 5, x minus 6. That was a lot of factoring. But here's where the fun part comes in. I know what you're thinking. How can this be fun? But look at the entire numerator and look at the entire denominator. What can cancel out, everybody? Yeah, this one's a really fun problem. All right, so there's an x minus 5 up top and an x minus 5 on bottom. Those would cancel out because those divided by each other equals 1. X plus 1 on top, x plus 1 on bottom. Those are gone. Anything else? X minus 6, gone. x plus 3, also gone. In the numerator, I'm left with 2 times 2, which is 4, over a 4 on the bottom. What's 4 divided by 4? Oh. Your final answer is 1. How crazy is that, right? Anyone think that ever happened? Like, look at what we had with that we started. That insanity that you're like, well, I'm not even going to write that example down. It's way too much. But that whole thing simplifies to just 1. Wahahaha. That's awesome. Good times, right? Good times. Any questions? Besides, why am I so evil? That wasn't evil. That was fun. Come on, be honest. Didn't you like crossing stuff out? A little bit? A little bit? Oh, division. There's an entire new operation we're going to learn today. Oh, that's terrible. How could I do this to you? That's insane. There's only 20 minutes left in class. We have to learn a whole new skill. Oh, my goodness. But wait a minute. Dividing by a fraction, that's actually not a new skill. We've divided by fractions by 4 before. And dividing by a fraction is the same thing as multiplying by the reciprocal. Remember, the reciprocal just means you flip the fraction upside down. So the numerator and the denominator just switch places. So this expression I have, or this division problem, 8x squared y divided by 15a squared b, like that's your first fraction. And it's being divided by this other fraction, this 2xy squared over 5ab to the 4th. So this is originally a division problem. But the very first thing I'm going to do is make it into a multiplication problem, because that's what we've already learned today. And that means that it's not really a new concept. Now, the first rational expression will stay the same. So this is still 8x squared y over 15a squared b. But instead of division right now, I'm changing it to multiplication. So I'm going to take that second rational expression and just flip it upside down. So now I've got 5ab to the 4th is going to be in the numerator. And the 2xy squared is in the denominator. Nice and easy. Maybe. I'm not familiar with that. Oh, fantastic. Copy, change, flip. Anyone else heard that before? From middle school? Cool. Copy, change, flip. Copy the first one, change the sign, flip the second one. Yeah, whenever you're dividing two fractions, you copy, change, flip. Cool. I like it. Now it's a multiplication problem. So start by just making it one entire fraction. And I'm going to multiply coefficients together. So first in the numerator, 8 times 5 is 40. In the bottom, 15 times 2 is 30. And we'll be able to simplify that in a moment. But when I look at the variables, I can simplify, any numerator with anything in the denominator. So I'm looking at like the x's. And think of this as one gigantic fraction now. Where are there more x's, on the top or on the bottom? So look right here. There's an x squared. There's x to the first. There are more x's up top. How many more? One more. One more x up in the numerator. Where are there more y's, top or bottom? Bottom. How many more? Just one of them. All right, how about A? Where are there more A's, top or bottom? Bottom, how many more? Just one of them. And finally, B. Where are there more B's? Top, how many more B's? 3 of them. Final step, simplify those coefficients. 40 and 30 are both divisible by 10, so you just take off the zeros. And we've got 4x b cubed over 3y a. If you put those in alphabetical order, that's fine. If you don't, I'm not going to mark anything. And that's simplified all the way. So division is really just multiplication. It's not an entirely new skill for you. All right, try this one on your own. Please pay attention to the operation. This is division. And even give you a little hint up there, reminding you to factor things first. Break them apart. And of those 4 polynomials up there, everybody, 3 of them can be factored. That's right, 3 of them can be factored. See that last one, the little sneaky guy? So factor each of these. It's like before I rewrite it as multiplication, like when I write it as multiplication, I'm going to factor it all at the same time. Like when I rewrite that first numerator, write it in factored form right off the bat. And then when you write that second fraction, make sure you flip it because it's division. And write that in factored form too. Make it a single fraction and just start canceling stuff out. Yep. Now what are those 2 numbers? So just pick 2 numbers that multiply to this and see if they add up to that. Good deal. All right, I like what I was seeing. I'm going to take this first numerator and factor it. 2 numbers that multiply to -8 and add to 2. That's going to be an x plus 4, x minus 2 over that trinomial on the bottom. I'm going to write that in factored form as well. So 2 numbers that multiply to 3 and add to 4 would be 3 and 1. Just as x plus 3 and x plus 1. I'm going to extend my fraction bar because I'm multiplying, but I'm not multiplying by the same way this is written. I'm going to flip it upside down. And so I'm going to take this denominator and move it up to the numerator. But I'm going to factor it first. And 3x and 3 have a common factor of 3, which leaves us with an x plus 1. And finally, that original numerator is now going to become the denominator. X minus 2. There's no way to factor that one. And from here, we just have a cancel party. I've got an x minus 2 and an x minus 2. X plus 1 on top, x plus 1 on bottom. I'm just going to rewrite everything. Always move your coefficients to the front, so the 3 moves in front, leaving us with x plus 4. And the denominator, we have x plus 3. Nothing else to simplify, and that's it. That's division. Hopefully this is not too scary for you. But in all honesty, practice this, and it's going to become so simple for you. Especially factoring. You've got to practice factoring to get better at this. Questions on this one before we move on? There's some other weird types of fractions you might see, but it all comes down to this same style, the same format. Complex fraction. I know, it's scary. Complex fraction. Here's all you need to know. If you see something like this, just think of it as like one fraction, divided by another fraction. Okay, so it's just, I'm using the fraction bar to represent division. Instead of the division sign, it's still going to be that same thing. Your copy, change, flip, if you will. Think of it as a numerator fraction and a denominator fraction. So that fraction up top becomes your first fraction that you don't change. This is still 5x squared minus 20 over 2x plus 2. But I'm now making it multiplication by the fraction on the bottom, which was being divided, because that fraction bar signifies division. So I'm going to take that bottom one, the 10x minus 20 over 4x, and I'm going to flip it. I'm going to take its reciprocal. So I'm multiplying by the reciprocal of 4x over 10x minus 20. All right, so you might see it written that way. It's still just division. You're still just dividing fractions. We can factor these. 5 and 20 have a GCF of 5, leaving us with x squared minus 4, 2x plus 2 has a GCF of 2, making this x plus 1. Four x is just 4x. Ten x and 20 have a GCF of 10, leaving us with x minus 2. Did I factor this all the way? Or is there something else that could be broken down a little bit further? Anyone see it? The coefficients, right? We can multiply and simplify those. But actually, look at those binomials. There's one binomial up there that we could actually break down further. Yeah, x squared minus 4. That's the difference of squares, isn't it? Aren't those both perfect squares? So I can take that first numerator with the 5, x squared minus 4. What does that break down into? Yeah, take the square root of each of those. It's an x plus 2 and an x minus 2. And then that 4x, 2x plus 1, 10, x minus 2. Let me move that up for you. And then just multiply all those coefficients together, bring them out in the front. So 5 times 4x is 20x, x plus 2, x minus 2, divided by 20 times x plus 1 and x minus 2. Does anything cancel out? And what else? All right, x minus 2 top and bottom, 20 top and bottom. We're left with x parentheses x plus 2 over x plus 1. A lot of steps, but each step individually is pretty basic. It's a basic skill. Carson? Okay. Do you see it? I did that back in the first step. So like from right here, when I see this bar means division, right? A fraction means division. And so this numerator stays the same. See how I didn't flip anything? Yeah. But this denominator, I did flip right here because I changed it to multiplication. So this 10x minus 20, it was technically in the numerator of this fraction, but look at how I moved it to the denominator of that fraction. That's where I flipped it back in the very, very first step. And that's what you want to do. Get rid of the division sign right away and make it a multiplication problem. Don't you guys want to see my next example? It's not that bad, right? That's harmless. I'm getting all these weird glances like, does he really expect me to keep working? I don't know. Do you want to learn this? Do you want to be successful? Do you want to pass your test? It's up to you. I can't force you to take notes or practice. It's all your decision. Did you learn what I wanted you to learn? So that's your division sign. So I'm going to leave that top fraction the same. The 4x to the 4th over y to the 6th. But here's where I'm making the change. I'm changing it to multiplication. And I'm taking this, this denominator fraction, and I'm flipping it right here. So the denominator of that red fraction is technically the 4y to the 6th. So I'm putting that up top. right? I'm flipping it right here. The 2x, technically that's in the numerator of that bottom fraction, so I'm writing it down there. 4 times 4 is 8, divided by 2 is 4, 3 more x's up top, and the y's cancel out. 4x to the third. All right, everybody. Here's your last. Oh, don't worry, I wasn't going to make you do that today. See you all tomorrow. By the way, you should really do some practice tonight on Delta Math. It'll be awesome. You're going to love it. It's going to be fun.